Hope everybody is warm and safe. Before I continue, any questions from last lecture? No questions? Are we good to go? Can we continue? Okay, thank you, Nicholas. So I would really appreciate if anybody would turn on their camera and show their face, because it'll help me actually talk. Thank you, Bradley, Jonathan. Okay. All right. So last lecture we were talking about probability density function for both discrete and continuous distributions. I want to make a quick summary of what we did last time, and also add a few items and give you a table that is nice and compact and has all the important concepts in this chapter 4 in one place. So we want to know what is probability density function. It is the probability that the random variable takes on a specific value. That is for discrete distributions. In the case of continuous distributions, where the random variable can assume real number values, f of x dx is the probability that the random variable assumes a value in the interval, which is x to x plus dx. So it's not just the function. This function is called probability density function. F of x dx is the probability. Okay, if you want, I can add that. F of x is the probability density function, and f of x dx is the probability that the random variable assumes a value in a said interval. So the cumulative probability function, it is like summing all the probabilities from the beginning until that point. So when you write f of x, that means it is inclusive of all the probabilities starting from the first possible outcome to that outcome. I'm saying very generally first possible outcome because counting is just relative. You can start counting from 0, you can start counting from 1, you can start counting from 453, and you can go on up to 524. It's all arbitrary. So it's not like 1 is always the beginning, 0 can be beginning, -5 can be beginning, anything can be the beginning. What matters is a discrete random variable is defined as what? What is the defining characteristic of a discrete random variable? A discrete random variable assumes values that are in specific steps, like integer. It can be only in steps of 1 to, let's say 1. So it can be as integers. It cannot have decimal points or uncountable numbers. Anyone can anyone tell me or give me an example of a discrete random variable other than a dice or a coin? If you are into the physical sciences and physics, what is the most famous quantity which occurs only in discrete units of or multiples of something?
What about like the Fibonacci sequence?
Fibonacci sequence is not random, especially because it is actually described by a formula that you can use to calculate subsequent numbers. It becomes progressively difficult, but that doesn't make it random. Yes, Jonathan.
Could you say like population, like the number of certain people or children or something like that?
So the number count of objects is always discrete, but how does it make it a discrete random variable? Just because something is discrete doesn't make it random. So how will you make the connection? That's what I'm asking. So going back to my physics example, if you take let's say you sample rain droplets, they'll all have certain number of charges on them. And if you do the measurement carefully, you do know that charge always occurs in multiples of the electron constant. So the charge on an electron is a number. In nature, you can only find charges that are multiples of the electronic constant. It can be 2 electrons, 10 electrons, 500 electrons, 10,000 electrons. but never like 0.3 electrons or 0.1 electron. Okay, so charge on objects is a very famous example of a discrete distribution which occurs only in multiples of E. Okay, continuous distributions there are many. I don't want to go into that. We did talk about it last time. So cumulative probability function in discrete notation, it is written as the sum of the probabilities from the beginning until that point. And in continuous, it is from -infinity to the value of x at which you are interested in. If this x is set to infinity, that is plus infinity, you are summing up over all possible outcomes, and that will give you 1, which is like saying sum of all the outcomes is 1. It's true for both continuous and discrete. And in fact, everything that we say or a concept that we define, it's true for both types of distributions. They just have slightly different mathematical notation. It's like saying discrete distributions are written as sums, whereas continuous distributions are written in terms of integrals, which are kind of convertible. Okay, can we continue? This is sort of the summary until so far. All right, so then we'll continue the summary. So I'll copy this table, actually duplicate the slide. This is so much better. I'm going to do this even in class. I can generate a lot of slides. Okay, for discrete distribution, we want to talk about the expected value, or what is called as expectation or mean value. How do you compute that? So if you want to know the mean value of x, that would be mean value of x is given as the summation of each value of xi that occurs in the distribution, each discrete value that occurs, multiplied by the chance with which it occurs. So I'm going to start writing P of xi. P of xi is shorthand for is the chance that x, the random variable, assumes a value xi, so that I don't have to keep writing the uppercase, which is sort of confusing. So this is the expectation for a discrete variable. Can you make the stretch and tell me what is the expected value or expectation for a continuous distribution? What else should I add to this formula?
A dx.
Yeah, dx. That is, I need to multiply the distribution function with the random variable. So expected value of x is x multiplied by the chance that x will occur. Here it is x times p of x. Sorry. Here it is x multiplied by the chance that x will occur, which is f of x dx. So I'm going to write that out in words. X times the chance that x will occur, which is f of x dx. Oops. Okay, so same logic. So it's exactly the same thing. The integral is essentially a generalization of summation. Okay, that's all. With me so far? Is this landing? Are we going at the right pace? You want me to be slower, faster? Madison? Yes.
So in the discrete distribution, you have xi, and then in the continuous, you have just x.
Yes.
Can you explain like what's the difference between that again?
So for example, I'll write, for example, let's say xi is like a coin toss. It can assume values 1, 2, 3, 4, 5, 6. Okay. So I'm denoting the specific values that the random variable will take. In the case of, let's say, for example, let's say x is the height of people, where x can take continuous values, typically from 4 feet to 7 feet, let's say. It can take all possible values. So there is no point in denoting any one value of x. We just use the symbol x to denote all the continuous possibilities from 4 to 7. That makes sense?
Yes, thank you.
Okay, thanks. All right. All right, so expected value or the mean value is this. So if you want, let's say expected value of x squared, or what would you write? That would be, I'm going to write, instead of this x bar, I'm going to write x squared, oops, sorry, x squared, and I'll put that within a triangular bracket to denote it's the average or expected value or averaged over all possible values. That would be xi squared times p of x. That is the value of x squared multiplied by the chance that x will occur, and whatever the chance of x is, that is multiplied by x squared or weighted by x squared. That's the expected value of x squared. The same thing will carry over here, where I can write the expected value of x squared is, to replace this, I should change this x to x squared. Now I'm taking x squared and then I'm weighting it by the probability that x will occur, or I can look at the probability of x and weighting it by x squared. In either case, I'm getting the expected value of x squared. Okay, this will be very interesting and useful if you are measuring a quantity, like for example, let's say you are measuring the size of the snowflakes that you can find out in the snow right now. If you go and look and try to do a measurement, if a snowflake has a, let's say, a radius or a diameter of a certain number, that is the distribution of diameters. But with the distribution of diameters, if you are asked to comment about what is the distribution of area, that is, what area do these snowflakes occupy, you can almost easily say the smaller snowflakes will occupy lesser area than larger snowflakes. That's obvious. But how much larger? If a snowflake is twice the diameter, how many times higher is it in area? If something is 1 millimeter and some other flake is 2 millimeters, how much more area does the 2 millimeter snowflake has? Area scales with what? Is it diameter or diameter squared? Hello?
Diameter squared.
Diameter squared. So if a circle of 1 millimeter has, let's say, pi times 1 squared, that is pi units of area, a circle of 2 millimeter will have 4 pi or 4 times more area. So this calculating or knowing how to calculate the expected value is really important when you are primarily measuring a quantity, but you are interested in higher order powers of that quantity. So if I were to quickly generalize this, what is the expected value of, let's say, x power n, where n is any positive value or positive integer, or not integer, positive number? I would, if I want the expected value of x power n, that would be xi power n times p of x, or in the continuous side, that is x power n f of x dx. With me? Is that you're able to generalize? Yes, no?
I understand how the scaling works, but not why we have these. So we have an x being multiplied once, and then there's an x squared, and there's an x to the n. What's the significance of that?
The significance is, the significance arises only when you have some tangible example that has a relevance. Like for example, if you are given, let's say, a collection of pebbles, like let's say spherical objects whose diameter could have a distribution, the larger sizes have a disproportionate fraction of the mass. Why? Because mass scales with volume, and volume scales with diameter cubed. If two pebbles differ in size by a factor of 2, they differ in mass by a factor of 8. So the idea of expected value is, like I said, you try to measure what is easy, which is measuring diameter. But from that, if you want to calculate some higher order quantities, you use this concept.
Okay, thank you.
Sure. So we can talk about expected value of x power n. We can also, we can also take this one step further. Actually, I'll write it here. We can take this one step further. Expected value of any function g of x. That would be the average value of g of x. Average value of g of x is g of x multiplied by the probability that x will occur, or g of x f of x times, g of x times f of x integrated over the entire interval. Okay. I'll try to pick some examples which illustrate this, but usually this g of x function is called a weighting function. Oops, sorry. G of x function is called a weighting function. Okay. And that function, it could be anything. Again, it's contextual. Until we find a context, it won't be very clear. So let me keep looking for an example to illustrate that. Okay. All right. And those examples will come when we have when we move from a totally abstract discussion where p of x is just very general and f of x is just a definition. I want to now talk about a specific example of a distribution for p of x and a specific example of a distribution for f of x, so that all these can actually be reinforced through some numerical calculations. Okay. So what we are going to see next is a discrete distribution, specifically called the Poisson distribution, which is quite interesting and something that I really like using in my work. I'll tell you why, though it's interesting. Okay. All right. So this is covered in section 5.2. All right. The Poisson random variable. Poisson random variable. Let's say x. Sorry, I should write it as a random variable x is said to follow the Poisson distribution, okay, if its probability density function is given by p of x equals I is equal to e power minus where is lambda? E power minus lambda power I divided by I factorial, where I can take values starting from 0, 1, 2, all the way to very high numbers. Okay. So this is the Poisson distribution function. Obviously, the French mathematician Poisson came up with this. The interesting question is how? How on earth can one person write this down and say it will describe the distributions of probability of natural processes or it typically is used to describe the probabilities where X is the number of events of a natural, usually natural, sometimes also engineered process defined by the average rate of occurrence lambda. That is, lambda is called the average of the Poisson variable. If you for a given average, what is the probability that X assumes values of 0, 1, 2, 3, 4, 5, and so on, to however large the number of possibilities are? How on earth would one be able to come up with this, or any type of these distribution functions? What do you think? Cut the answer short. It's usually a combination of observations plus mathematical intuition for the type of function, that would describe this these observations. So that is the territory of mathematical geniuses, which we will stay clear of. Okay, so we have this Poisson distribution function, which goes as exponent of minus lambda power I divided by I factorial, where I can assume values of integers starting from 0. Okay. The first check you want to do is, if you add up these possibilities of I equals 0 to infinity, will it add up to 1? That's the first check of any distribution function. A probability distribution function has to add up to 0. All the possibilities have to add up to 0. Okay, so let's first check that. So if I write this function, and I have to sum this up from I equal to 0 to infinity. That would be the summation So P of x equals I is nothing but the formula that I gave you. So you have to expand this summation and see if this will add up to 1. That's the goal we have here. Okay, so let's do this like very humble engineers who don't know a lot of mathematics. At least I don't. So I'm going to write e power minus lambda is a constant. It has nothing to do with I. So I can just write that outside the summation. And what's the first term? I equal to 0, lambda power 0 divided by 0 factorial. I'll write it even though we all know that lambda power 0 is 1 and 0 factorial is also 1. Okay, plus what's the next term? Lambda power 1 divided by 1 factorial plus what's the next term? Lambda squared divided by 2 factorial plus obviously third term is lambda cube divided by 3 factorial plus and so on. It'll go on. Okay, so this is the first term remains e power minus lambda. And then I have this is 1 lambda power 0 divided by 0 factorial. And then I have lambda divided by 1 plus second term is lambda squared divided by 2 factorial plus lambda cube divided by 3 factorial plus and so on. Anybody recognize this function from Taylor series? Or if you expand a certain function, you will get 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x power 4 by 4 factorial and so on and so forth. Which function's expansion is this parenthesis here?
Is it Stein?
No. It's not sine. It was on the mock prerequisite quiz that I gave, I think. So this is the Taylor series expansion of e power lambda. I mean, it's if you write it out, you can see that, and I'm just going to take this and say wherever e power minus wherever this parenthesis appears, I'm going to replace it with e power lambda, which completes our quest to see that whether the probabilities all add up to 1 or not, which they do. So if you start the counter from 0 and keep counting to infinity, all the probabilities will add up to 1. That's what this proves. So this is good, which means this checks out and all the probabilities add up to 1. Okay. Now let's pay a little bit attention to this parameter lambda. Lambda is the mean parameter of the Poisson distribution. It's like saying the expected, not it's like saying, it is the average or expected value of I. Average or expected value of I. Okay. Let me ask this question. What is the average number of hands, like arms, that humans have? What is the average number of arms that humans have? All humans. Average number.
2.
2. Okay. Any other responses? Slightly less than 2. Okay. Interesting. Any other responses? Okay. We'll start with slightly less than 2. If I expand the question by asking, what are the possible number of arms humans could have, what would be your response?
Like 4.
2.
Most of us have 2.
Deformation.
Sorry? Come again?
If there's like a birth defect, you could have up to like 3 or 4.
Okay. So you're saying 3 or 4 is possible. We'll take that. Let's rule out anything 5 or above is not possible. Okay. We'll take 3 or 4, which is rarest of rare. Very common is 2. There are some people who have either kind of congenital defects or they lost an arm during life, So there are some people who born defective, say 0 to 4, like John said. So if that being the case, the average cannot be 2. Would you agree with me? There are some folks who don't have 2, they have 1 or 0, unfortunately. And then there is the rarest of rare, where there are 3 or 4, but I'm guessing there are not many of them, maybe like 1 in 10 million, 1 in 100 million kind of ratios. So the average value of the number of arms that humans have is definitely not 2. It's somewhere between, let's say, 1.8 and 2, maybe, or 1.6 and 2 at best. That is the interpretation of lambda. Lambda is the average or expected value. It is not the value that an individual would have, but it is the average of all possibilities in that population. Is that clicking? Can you try thinking about an example where you talk about an average, it has a certain value, but it's not the value that any one person can have, because it's a decimal point, whereas the Poisson variable can have only discrete values.
It's like an average number of kids in a household. It'll probably be
Average number of average number of kids in a household is maybe in the US there are about 1.8 kids per household. I'm just making it up. I don't know for sure. But how can you have 1.8 kids? That's not possible. Either you have 0, 1, 2, 3, 4, 5, 6 up to 10, maybe 12 kids. So Poisson can only be a solid integer. By solid, you mean a whole number? Yes, absolutely. It can only be an integer, a whole number. It cannot be a fraction. Okay. How many of you have heard of this number, fertility index, or replacement level population growth? Is lambda like the X bar for a discrete random variable? Yes, it is. It is exactly the mean value. That's correct. If you actually work out I times P of Xi, you can show that it is equal to lambda. I'll write that down here. Lambda. How many of you know about fertility index and replacement level? So fun fact. So to have a population heard of fertility in the relation of politics, but not math. Well, politicians know more mathematics than you do. I mean, you and I do. So they use it to their political messaging. So, okay, fertility index is essentially the number of children all women in the childbearing age can produce in a population. Like if you think childbearing age is 16 to 50, they say that if you want your population to keep growing and not falling, you need at least 2.1 children per woman. Of course, nobody can have 2.1 children. What it means is in a population, if most women have 2 kids, some women have 3 kids, and a fewer number of women have 4 kids, it will compensate for those that have only 1 kid or don't have any kids. So this mean parameter is sort of a number which anchors the Poisson distribution to a certain range, so that you can see that if a mean is let's say 0, if the mean is 0.1, what does it mean? It means if you take 10 shots, only one of them is likely to hit. But it doesn't mean only one is the possible number of hits. If you take 10 shots, okay, let's do this thought experiment. Let's say we all go to a firing range and we all take 10 shots each. And some of us are very good. We may make 10 on 10. Some of us are extremely bad. Let's say we make 0 on 10. And then there will be some which make 3, 4, 5, some distribution. So if we count how many shots that each of us was able to make, and then average it over this 41 class of students, the number could be something like 3.2. It means the spread is around 3. Maybe most of us are making 3 or 4 shots, but then there will be some who made 10 shots, some who made 0 shots, and it's a distribution. Is this relatable, or you're able to understand what this lambda means? Yes, no. Yes, Rashid, thank you. Jonathan. Yes, Madison.
So you said that lambda has to be a whole number. And for
No,
the
no,
example,
no. Lambda can be a real number. It can have decimal points. It need not be a whole number. The value of the Poisson random variable has to be a whole number.
okay.
That is, if you take, let's say you made 4 shards, that is a 4. That cannot be 4.1 shards, but the average number of all of us can be 4.1. Okay. All right. So let's do a problem in Poisson random variable to kind of understand this a little bit deeper, better. One second. Problem selected here. Okay, I'll give you a problem here. Okay, so here is my one of the examples that I introduced earlier. In the San Francisco Bay Area, the chance of or the rate of earthquakes occurring based on historical records in the last 200 years is about 1 every 30 years. Okay. If I live in that area for a period of, let's say, n years, I'll give different values of n. That's why I'm keeping it as n. The average number of earthquakes I would experience is lambda equals 1 every 30 years, right? One quake, sorry, lambda equals 1 divided by 30 times n years. So the reason I write it this way is 1 quake divided by 30 years times n years, which will make this n divided by 30 quakes. Is this train of thought making sense to you? You have to kind of measure an occurrence rate. That occurrence rate is 1 in 30 years in this case, multiplied by the time for which you are conducting this experiment or observation, which is n years. So the average number of quakes in that n years is expected to be n divided by 30. N can be 20, 30, 60, whatever number of years we spend there. Okay. This is the average number. The question is, what are the probabilities for each to happen? So now let's be specific. Let's say n equals 15 years, which makes lambda equals what? Which makes lambda equals
Half.
15 divided 30, half, like 0.5. Okay. So if lambda is 0.5, compute the probability of I equals 0, 1, 2, 3, 4 quakes experienced. This is where we put the formula to use and actually do the calculation. Probability of I equal to 0 is e power minus lambda or e power minus half times lambda power I, which is 0.5 power I being 0 in this case, divided by 0 factorial. So this is e power minus 0.5, which I need a calculator to calculate. That's 0.6065. 0.6065, or that's about 60.1%. So if you live there for 15 years, there is a 60% chance that you won't experience any earthquake. That's the interpretation in words. Is that interpretation landing? That is, if the average is 0.5, the chance of nothing happening is actually 60%. Yes?
Yes, it makes sense.
Makes sense. Thank you. Thank you, Elias, Nathaniel, Madison. Yes, question. Nathaniel, is that question or you're just saying yes? Okay. All right, good.
I have
Okay.
a question.
Yes,
Can
go
you
on.
explain the 0 factorial to me? Because I thought anything that was divided by 0 is undefined.
So 0 factorial in the field of combinatorics, they define it as 1. So 0 factorial, wherever it appears, we just say it is 1, but it's a definition. It's like, okay, they all agreed that it is going to be 1. Other than that, I don't have more information on. It's not dividing by 0, it's dividing by 0 factorial. That's the difference I have. So other than that, I don't have any more insight on why is 0 factorial 1.
Okay, thank you.
Yeah. I don't know it, and I want to share my ignorance with you. All right. Probability of I equal to 1, or in other words, the chance of experiencing exactly one earthquake would be e power minus 0.5, 0.5 power 1 divided by 1 factorial. This is like saying this is e power minus 0.5 divided by 2. Or in other words, the probability of 0 quakes divided by 2, which is about 30.1% if I round off to 1 decimal point. So 60% chance nothing will happen, 30% chance that there will be exactly one earthquake you get to experience in 15 years. Okay. What else do we know about sum of all the probabilities? 0, 1, 2, 3, 4, 5, 6. Everything should add up to what? 1. So we have already seen 90% being spoken for. 90.2% of the probability is already spoken for. Remaining, we have only 9.8%. So think about how nonlinear this distribution is. Only 0 and 1 have 90.2% of the chance. So all the remaining possibilities are squished into 9.8%. Okay. Continue computing. Probability of I equals 2, which is e power minus 0.5 times 0.5 times 0.5 squared divided by 2 factorial, which is like saying the probability of 0, 0.5 squared is like saying divided by 8. Or in other words, this is 60.1 divided by 8, or that is 7, and then there is a 4.1, that is 7, roughly 7.5%. I can be precise, but that's not the point. It's about to see how nonlinear this thing is.
I'm sorry, can you tell me what you did with the 2 factorial?
2 factorial is 2. 0.5 squared is 0.25. So essentially, I'm getting a 2 times 4 in the denominator, that is 8. So I just said it's 1/8 of P0.
Okay, I got it. Thank you.
So I said remaining 9.8% is all the other outcomes, and 7.5% is already gone. So we have now accounted for 97.5% of the probability with just only 3 outcomes. So if I ask you the question, what is the probability that you will experience 3 or more quakes in just 15 years of living there? That would be what? About 2.3%. Can you follow how I got the 2.3%? Or are you able to see how I got the 2.3%? Yes, thank you, Elias.
I'm sorry, can you explain how you got the 2.3%?
So I'm asking for the probability that I will experience 3 or more earthquakes in those 15 years. I've already accounted for 97.7%. So anything else that's remaining is within the 2.3%. 3 or more is 2.3%. So that's
Okay.
where that's coming from.
Gotcha. Thank you.
Is this making sense? Others?
Yes.
Yes, thank you. Thank you. Okay. All right, good. So if you graph this or if you tabulate this, it's going to look something like this. You can try graphing it, but I want to move on to another example. But let's say I equal to 0, that is 60%. So if you are in elementary school or middle school learning how to graph for the first time, if this is 60%, the next probability is 30%. It should be roughly half of that. I equal to 1. And the next probability I equal to 2, this is 7.5%, which is 1/4 of 30%. Is that correct? That's correct. That's 1/4 of 30%. So this whatever this height is, I should draw something that's only about, maybe I won't pass middle school. Let's see. Yeah. This is 7.5%. And everything else that you draw after here, they all add up to 2.3%. That's the implication of this number. So this distribution is very nonlinear. It quickly drops because of this exponent factor. But that's the point. It's a very accurate description of these rare events, because think about it. If you are there 15 years, 60% chance that nothing will happen, which makes all of these by definition rare events. All these are together only 40%. And if you define a rare event as what are the chances that you will experience 5 or more quakes, that's what, if you define as rare, you would see that it's actually extremely unlikely. Okay. Usually this Poisson distribution is used to model rare events like earthquakes, natural disaster, plane crashes, terrorist attacks, or global pandemics, or stuff that happens very rarely, or asteroid impacts, those kind of processes where you have some measure of the historical occurrence rate based on some data. That is, in this case, 1 every 30 years. And then it is like a period where you are interested in observing. That is very important. If you think about asteroid impacts, for example, let's say there is a deadly asteroid impact every 800 million years, 800 million with a M, 800 million years. Okay. How long do you think humans have been active as a civilization, or humans have been active as a species? Do you know? Like, what's been our total lifespan for humans? it's a give or take a few million years. Let's say for simplicity, we'll say 1 million years. Okay. So the chance of a asteroid hitting is 1 every 800 million years. And for the period that we have been active, which is, let's say, 1 million years, the chance is, you can compute it. The chance would be 1 every 800 million years times the 1 million years that we have been active. So it's about 1 in 80. 1 in 80. So that is lambda for this case is 1 over 80. So if you are observing over a period of 1 million years, what are the chances that you will observe, or what are the chances that nothing will happen? So lambda for asteroid impact is, I should start from here, rate of occurrence of asteroid impact is about 1 in 800 million years. Okay, we have been active as a species for 1 million years. So lambda for asteroid impact is one impact, average number of impact. Lambda in this case is average number of impacts is 1 over 80. So the probability that nothing bad will happen, P of 0 is exponent of minus 1 over 80 times power 0 divided by 0 factorial. What is this number? Can anybody compute and tell me? That's 98.75%. Very good chance that nothing bad will happen to us. How about that? 98.75% that we will never see an asteroid striking Earth when we are around. Okay. But of course, if you want to compute what's the probability that there will be exactly one earthquake, is the answer 0? That can you say for sure there is no chance that there will be an asteroid impact? You can't say for sure because there is about a 1.23% chance that there will be one impact over 1 million years. 1% chance. Two impacts, that's even smaller. 3 impacts, even smaller. But one impact, 1.2% chance. Okay. So this Poisson distribution is actually quite also useful in applications, modeling defects, or modeling the rate of occurrence of defects in quality control. So if you are producing batches of, let's say, 10,000 articles per day, the rate at which you might, or the number of bad products or badly manufactured products is usually modeled as a Poisson variable. So there is a lot of application in quality control and metrology for Poisson distribution. Okay. So what I would suggest is the book is sort of lean on the number of problems related to Poisson. Please work through all the examples that they have done. Okay, I'll try to bring one more example next lecture, but today I want to move on to normal distribution, which is another important distribution that we have to learn. Okay. Any questions so far? Is it making sense of the examples that I'm trying to provide?
Yes.
Thank you, Madison.
So
Yeah.
for the example we just did with the species and the asteroid.
Yeah.
So is this the chance of an asteroid hitting Earth while all of human, like like the entire history of humans is, or is it just like how likely it is to hit us?
It is over this 1 million period. If you ask the question, will it hit in the first 1,000 years or last 1,000 years or some middle portion? That is a good question. That it does not describe that. It treats the entire period like one unit. It's 98.75% chance that it will never happen in that 1 million years. If it happens, when it will happen, it's another sub question to model whether that distribution is linear in time or non-linear in time. That maybe that is also something we could model as a Poisson distribution. So if you start with here, let's say, for example, 1.2% is the chance, or 1.2% is the chance that something bad could happen in a period of 1 million years. So let me think here. Yeah, I haven't thought about how to interpret it in the time domain. It's like if you look at an atom which is radioactive, we know it will emit a radioactive particle like an electron or a alpha nucleus, and it will decay. But when it will emit, there is a certain distribution that predicts the time evolution of processes. I don't exactly remember it on top of my head, but I can look up and get back to you. There is a distribution which predicts the timing sequence. I don't know that.
So if we had to use this to help us understand what the chance is of hitting us right now, how would things change with this problem?
What is the chance that something? Okay, so even that I think is modeled as a Poisson distribution. It's like asking, let's say you start counting time, like out of those 1 million years, a certain fraction of years has already happened. If the event took place in the first that portion, or will it happen in the remaining portion? Because let's say we are looking at the chance of one impact. Already 400,000 years have gone, nothing has happened. So will it happen in the remaining 600,000 years is the question you are asking, or when it will happen in these remaining years. I'll have to think about how to model that, but there is a way to do that. It's just not something I am ready to talk about now because I don't have an answer for you.
That's okay, thank you.
Yeah. Good question. All right. So then we need to then talk about the other commonly encountered distribution, which is continuous in nature. So we are going to talk about the normal distribution. Okay. Oh, I wanted to paste one picture here. So for as far as this Poisson distribution is concerned, here is one picture that you should sort of etch in your memory, which will help you remember the shape of the distribution. Second. So this is figure 5.3 from the book in page 149. Okay, so I'm pasting this not because I'm very interested in this particular value of lambda equals 4, but what you should see is if you have a lambda parameter of 4 or 5 or 10 or whatever number, that approximately is the center of the distribution. Around 4 is where the distribution will hit a peak, and then it will decay quickly to the right side. It will rise, have a peak, and then decay. And the location of the peak is approximately scaling with lambda. If lambda were 10,000, you would have the same thing at 10,000. It will start to rise around 9,995 or something, and then quickly fall around just after 10,000. So Lambda is kind of the anchor around which the distribution is usually found to be non-zero. Okay, so that you need to remember. Lambda is approximately the value at which the distribution attains maximum. All right. So we have 25 minutes. Okay. Instead of starting normal distribution, let's do something else. All right. Let's talk about this very simple looking distribution called uniform distribution. Okay, the uniform random variable. It's like saying it is a distribution where the chance of any number in that interval occurring is the same. It's uniform. It's like just 1 over width of the interval. So in discrete distributions, we saw dice as a very famous example of a uniform distribution. All outcomes have the same probability. This is the continuous analog of that, where all the values are equally probable in that interval. So if alpha is 0 and beta is 1, the distribution or all the values have an equal chance of occurring. That's why this is called an equal distribution. Okay. Instead of asking you for an example, I'm going to show you how we use uniform distribution to actually compute area of shapes that are not easy to describe. Okay. Here's the problem statement. And by the way, this is not in the book. This is something I developed or wanted to talk about today to calculate area of shapes, let's say. So let's say we have a circle. Okay, we have a circle, and for a second, please tell me that you don't know the area of a formula for the area of the circle, that you don't know that this is actually pi r squared. You somehow don't know that formula, but you do know the, let's say, the shape of that curve, which is x squared plus y squared equal to 1. Okay, our goal here is to compute area, but not use the conventional formula, but a way to do this statistically. Okay, this type of a calculation is called Monte Carlo method, where you know the boundary. That is, if I arbitrarily, let's say I draw a square or some kind of a region around this shape, what I do know is if I pick a random point in that area, I can tell whether it is inside or outside my circle. How do I say that? If I just arbitrarily pick some random point, x0 and y0, how do I tell whether it's inside or outside?
Would it be more than 100%?
No, I'm just saying, imagine you are having a board of darts, like a dart, D-A-R-T, dart target. You throw an arrow. It can either land inside, outside, or maybe on the line, and we'll consider on the line as inside. So there are only two outcomes. Either it can be inside the circle or outside the circle. If you are doing this in a bar where there is a dart board and you throw a dart, you visually see whether it's inside or outside. And if, let's say, you took 20 turns, you hit some, you miss some. If I take random numbers, let's say I want to generate a random number in the x direction. So I have the line. Let's say this is minus L, this is plus L. Like my alpha is minus L and beta is plus L. I want to select a point which is randomly located on this line. I select the x value. And for the y direction, this runs from minus L to plus L. and I again select another random value. So if I choose two random numbers, I can define a point. Are you with me so far? Did you select two random numbers between -L to +L? You define a point in two-dimensional space. Okay. Once you have this point, how will you check whether this is within or outside a circle or an ellipse or hyperbola or whatever shape? How will you check it?
Couldn't you check it by like the one which in the circle equation?
Right.
If it's
If it obeys or not obeys the circle, that is if x0 squared plus y0 squared, if it happens to be less than 1, then it is inside. If it happens to be greater than 1 or less than or equal to 1, we'll call it inside. If it is greater than 1, it is outside. Or in other words, there is a binary outcome. Either it's in or out. Okay. So what is my goal? I want to know the area of this shape, but I don't want to do the regular mathematical formula. I want to do this statistically. So what I will do is I will pick a point, a random point, and check whether it's inside or outside. One point can't tell me anything. I'll do it many times, many times. What will happen is randomly, some of them will fall outside, some of them will fall inside. So if I do this, sorry. So randomly choose points, check if each point is inside or outside the shape, in our case, which is a circle. And then at the end, you can compute the ratio of in versus out. So if the number of ins is, let's say, in or I divided by total, okay, multiplied by the area of the square. This will give me the area that of the shape that I'm seeking. I'll bring this picture here. Okay, so I'm making the assertion that if I do this many times, and each time I check whether the point is within or outside my shape, I can get a ratio of the number of successes to the total and multiply that by the area of this square over which I'm picking dots. That will give me the area of the shape. Two questions. One is intuitively, is this making sense? Not making sense. Intuitively, are you able to agree? And if you're able to agree, why do you think this is correct? If you're not able to agree, please tell me. At least we can talk.
I don't see it yet.
You don't see it yet. Okay, let's talk about this. So let's start with this underlying square. Okay, so let me write this underlying square runs from -L/2 to +L/2, so that the length in each direction is L, and the area of this square is L squared. That's okay?
Yes.
Yes. Okay. So that's L squared. Okay. Within this L squared, I am dividing this square into two zones. One is the zone that I care about, and the other is the zone that I don't care about. That is the outside of the circle. Okay. When I have a square, if I close my eyes and I randomly pick a point, the chances are that I don't have any preference, that I'll pick up over time all the points because I don't have like any center region. I just randomly choose points from the square. I'll end up choosing almost the entire, like anywhere from here. I don't have a preference because I'm randomly choosing from the square. Is that okay? Okay, I can see you, Jonathan. Yeah. Okay, good. So yeah, but then within that unbiased number of points or unbiased area, I have a bias through which I define success. That is, if you are within the circle, you are a success for me. If you are outside my circle, you are not a success for me. So the denominator is introducing the bias. It has information about the shape that I care about, whereas the total has no information of the shape. It's just uniformly distributed throughout the area. So if I take this ratio, that tells me the ratio of the favorable number of points to the total number of points. And if I multiply that by the total area from which I am collecting these points, that should tell me the area of the shape that I am biased towards.
Okay, that makes more sense.
Okay. Others, how about you? Are you also able to follow?
Does L equal 1?
L can be 1. L need not be exactly 1. In fact, L can be any arbitrary value. The probabilities will scale with each other such that you will always get the area of the shape. And we'll see that in the MATLAB code that I have.
Okay.
Because if you make L like very big, the T also will become big and scale with it. So that in the end, you will anyway get the same answer regardless of what value of L you end up using. This is not in the book, by the way. So this is the only source where, not the only source. There are a few other sources of textbooks that you can find it. But anyway, yeah. Others, I just want to make sure before I show you the MATLAB code. Molly, Sean, Ansar. Chase, thank you. Elijah Sorin. Nicholas, Brian, thank you. Emiliano, thank you. Okay, good. Looks like people are agreeing with me. So this method, only thing you need to know is how to check whether a chosen point is within the circle or outside the circle. And it need not even be a circle. Like this whole calculation, it depends on having a baseline square. It depends on choosing random numbers. It depends on defining what constitutes success or favorable outcome versus unfavorable outcome. And you don't have to even use a circle. You can do a ellipse whose equation is x squared by a squared plus y squared by b squared equal to 1. It can be an ellipse. It can be any geometrical shape. Let's say, for example, I asked to calculate. Here is a parabola. And here is another parabola. Okay, sorry, my drawing skills are not the best in the world. So I want to know what is the area of this shaded curve. I know that it is contained between curve 1 and curve 2, but I don't know exactly how to compute it. What I can do is draw a square around that and just have a mathematical check for whether a chosen point in the square lies in this shaded region or outside the shaded region, and then apply this formula to get the area of this shape or this region. So it can be generalized pretty easily. But what I'm going to do is, I have 10 more minutes. I'm going to show you a code where I wrote it up to calculate what is the area of a circle, okay, whose radius is 1, to keep it simple. Okay, it's a unit circle, which means it runs from -1 to +1, -1 to +1 on x and y direction. And I'm going to draw a square of intentionally side 1.5, so that it's not exactly a unit square. It's a square of side 1.5. Sorry, I should maybe draw a side of square side 2, so that it runs from 2.5, so that it runs from -1.25 to +1.25 on either direction. Let me annotate that here. So I'm going to draw a square which runs from minus 1.25 to plus 1.25 and a circle which is, which is running from minus 1 to 1. Okay. All right. So I'm going to post this code. Okay. So area of the circle, as we know, is pi r squared. So this is pi times 1 times 1. That's like a reference value. And I'm running this loop for, let's say, 100 times. I'm choosing 100 uniform random numbers. Each time I check whether this point lies within the circle. If it lies within the circle, I increase the count by 1. And I do this for n times, where n is said to be 100 times. Okay. So if I run this, based on 100 random trials, the area that I get from my Monte Carlo trial is 3.3125, whereas the true area of the circle is 3.1416. So the difference is about 5.4%. That is, I'm getting 5.4 within 5.4% of the answer. If I increase the number of trials or number of data points, the statistical accuracy very quickly improves. If I do 1,000 trials, I can get only 3% difference. Okay, 3% difference. If I do a 10,000 trials, the difference is 1.24%. And if I do 100,000 trials, I'm within 1%. This is only 0.05% difference. Almost same as the exact answer. Okay, so you can be creative. Like you can start putting in ellipses or whatever shapes and use this as a method to compute the area of shapes that are not mathematically easy to do analytically. So this way of calculation is called Monte Carlo method for area estimation. Okay. I am planning to wrap up a few minutes earlier today. Any questions? We are going to start normal distribution next week. But on this topic of area estimation and Monte Carlo, any quick questions before we go? Yes, no? I know I might have gone through this a little bit quickly. I'm going to post this code. Please play with it and sort of convince yourself and come back with questions for next lecture or for Office 7. Bradley, is that cool? Good. Okay, Jonathan. Did schematically or in a big picture level, is this okay? Is it making sense? Or we want to redo this maybe next time? You're okay? Look,
It makes sense, but I have a question. What if all of your back to the dartboard example, what if all of your shots land inside the circle and none land outside the circle? Are you still able to use this method?
your dartboard has a certain bias, which is you. You are a shooter. You have your biases. Random number selection has no bias. So if you have a circle that is almost fully, if you draw a square around the shape that you want, eventually, that's the key word. If you put large number of trials, eventually you will get the area accurately. You just have to do lots and lots of samples.
Okay. Thank you.
Yeah, there is no bias here. The random number selection is uniform. When we are at the bar throwing the darts, we are the bias. Okay.
Understood. Thank you.
All right, good. So good question. Let's hopefully we'll be in class on Tuesday. I'll post this tonight. Please play with this MATLAB file. Try ellipses, try complicated funky shapes, and be creative with it. It's a good learning tool. This is how you learn. You don't have to write the code yourself, but start somewhere and get into it. Okay. All right. I have to depart few minutes early today. I'm sorry. Thank you so much. We'll meet on Tuesday. Thank you. Bye.
Goodbye.
Thank
See
you.
you Tuesday.
Thank you. Thank you.
you.
Have a good day.
Thank you. Have a good day.